For centuries, the transfer of architectural intent relied on physical artifacts. The drafting table was the absolute limit of design velocity. Today, the tools have digitized, but the workflow remains fiercely linear. A project moves sequentially from initial design into zoning and regulatory analysis, and finally into thermodynamic modeling. Because these systems operate in isolation, a failure at the end of the line cascades backward. If a thermodynamic simulation shows a building will fail to meet carbon-neutral standards, the geometry must be scrapped, and the initial drawing phase begins again. This friction is the inherited weight of decades of urban planning. In a dense environment, like New York City, every square foot carries a dense web of legal limitations and physical constraints. Modern development demands real-time, parallel processing of these constraints. Yet, the core methodology remains stubbornly sequential, bottlenecking the transition to sustainable infrastructure. The tech industry's proposed solution to this bottleneck is generative AI. Large multimodal models and diffusion-based image generators are heavily marketed as the future of rapid architectural iteration. But standard diffusion models are blind to physical reality. They calculate visual probability, arranging pixels based on patterns they have seen in training data, without any underlying mathematical representation of gravity, load paths, or material strength. When a system optimizes entirely for surface-level aesthetics, it generates geometry that cannot survive in the physical world. True automation in the architecture, engineering, and construction sector requires a different mathematical approach. The system must predict the engineering logic of a space before it attempts to render the image. The virtual building has to solve for its own physical and regulatory constraints before a single pixel is visualized. Consider how an autoregressive model constructs an image. It guesses the next visual token in a sequence based on the tokens immediately surrounding it. Because it lacks a holistic understanding of a three-dimensional environment, it frequently outputs visual gibberish. You get staircases that look correct locally, but terminate directly into solid, load-bearing concrete walls. The alternative is a joint-embedding predictive architecture, specifically tailored for spatial logic, a vision language JEPA. Instead of predicting pixels, this architecture maps the semantic meaning and physics of a structure in latent space. This latent map acts as a veracity filter. If a proposed layout violates physical forces, the system rejects it, forcing a geometric recalibration. By solving the physics equation in latent space, the model makes structural viability an absolute prerequisite for visualization. Physics is only half the equation. An architectural concept must survive across two distinct scales: the macro-level constraints of the urban environment and the micro-level performance of individual materials. To coordinate these vastly different datasets simultaneously, the platform utilizes hybrid vision transformers, or ViTs. Within the transformer network, global context attention heads scan the broader site plan, locking in boundary parameters and solar orientation. Simultaneously, local detail attention heads lock onto microscale requirements, analyzing specific properties like insulation R values or loads for a geothermal heat pump. This multi-manifold calculation collapses the traditional gap between a building's legal site limitations and its actual thermodynamic performance. Even with structural and legal viability solved, a commercial platform must still produce designs that reflect a specific architectural identity. This is achieved through an ethos encoder. It maps a firm's specific portfolio, their preference for natural materials, visual contrast, or precise space utilization, into a dedicated mathematical space known as a design manifold. When a client uploads unstructured data, rough sketches, voice memos, or disparate reference images, the system translates that noise to the nearest valid coordinate on the firm's specific design manifold. To keep this process efficient, the architecture employs selective decoding. The model only executes computationally expensive visual updates when a core functional constraint is altered. The result is a system that maintains high visual integrity and consistent aesthetic style, while cutting processing latency down to a fraction of traditional rendering times. When these technologies combine, the interface between architect and machine shifts entirely. The months-long loop of drafting, testing, failing, and redrafting collapses into a single, continuous, multi-manifold calculation. The joint-embedding predictive architecture guarantees structural logic. The hybrid vision transformers synchronize the urban scale with the material scale, and the ethos encoder locks in the aesthetic signature. The resulting output is not a hallucination of pixels. It is a calculated geometry that has already satisfied its own physical and regulatory constraints. The bottleneck in the built environment will not be solved by drawing faster. It will be solved by calculating the mathematical reality of a structure at the moment of its conception.